So I'd like to go ahead and look at this question. This question was a bonus question on your test. And the only reason why I made it was a bonus question wasn't because I thought it was particularly challenging. It was just we hadn't done one like this. So I didn't think it was fair to ask it as a straight up test question. But as far as the content, there's no new content in this question. And so what I'd like to do is I'd like to work through it with you because I feel like we're still having some difficulties with these triple integrals. So this looks similar to that bonus question. You can see though what I did is I repeated the image 6 times for you so that you get to, so we can actually do some sketches on these. But what we're going to do is we're going to set up all of the different triple integrals that we can in the rectangular coordinate system. And so if we've got a triple integral for our function of 3 variables, there are 6 different orders that we can do the integration in. Okay. So we're just going to assume that we're dealing with some integrable function here, f of x, y, z. So remember, just to reiterate, we can't imagine what this function looks like, or not very easily. We can't graph this function through the means of that we've usually sketched things. Why? Because this takes as an input 3 coordinates, x, y, and z, and outputs some 4th coordinate. Maybe you want to call it w or something like that. But there's no way I can even pretend to fudge to draw 4 dimensions on a 2-dimensional sheet of paper. There's just no way I could do it. Okay, so in this case, our solid, and let's go ahead and give this solid a name. Let's go ahead and call this solid E. So we've got this solid, and it's bounded by the planes y equals 0, z equals 0, y equals x. That's this, that y equals x gives us that beige face that you can see there. And then this cylinder, now careful, remember the cylinder is going to be so for every slice for any y value, so parallel to the xz plane, or for any y value slice, it's always going to look like this spherical, or excuse me, not spherical, elliptical cylinder. Okay. So again, we imagine this cylinder. If we were to give more of a sketch of this cylinder, here's the xz plane. In the xz plane, we have an ellipse, and it extends outwards. And so for any slice along any slice of a plane like y equals a, it's always going to look like an ellipse inside of that. Okay. So what am I asking you to do? Well, what we're asked to compute here, first of all, is we're trying to come up with different ways of computing this integral, which is the triple integral over our region E, which is this solid. Okay. So just to reiterate, this solid is a solid. It's not a surface. I'm not just talking about the points on the surface of this. I'm talking about all the x, y, z ordered pairs that lie within this solid and are on the boundary of this solid. Okay. All right. So the next thing I think is really, really helpful, and it's going to be helpful for this problem here, is to go ahead and sketch the traces in the xz, the yz, and the xy plane. So I'm going to go ahead and sketch their traces. So I'll start off with sketching the trace in the xz plane here. Okay. So the xz plane is where y equals 0. That puts us in this plane right here. Okay. So if we imagine what that shape looks like, and one way you could do that is if you were to shine, somewhere far out on the y-axis, you shine a light on it, and you say, what shadow does this make on the xz plane? That would give you that projection onto the xz plane. Okay. So if we were to project that onto the xz plane, now be careful here. You kind of have to manipulate this image to rotate us into the positive. This is the positive x-axis, whereas this is the positive x-axis here. But we'd have this shape right here, and this could be described by, well, let's go ahead and put some coordinates on here. So let's see here. This would be the coordinate 1, 0. This would be the coordinate 0, 2. And again, what we had when we shined a light onto this solid, the shadow that it makes in the xz plane looks like this picture here.
that be 0, 0, 2, or is it 0, 2?
Great, yeah, so I'm just doing this in the XZ plane here, Matt.
Okay.
And so I'm only giving 2 coordinates, and you're just going to have to, and this is something that I debated whether to do. I'm only going to draw 3 traces. I'm not going to draw 6 traces. So we're going to, at different points, consider X the independent axis and Z the independent axis here. Okay? But as I've written this, we'll treat X as the independent axis. So yeah, great question there. Okay, so if we want to go ahead and describe this upper region, so this is the shadow in the XZ plane, and if we were to describe this upper region here, we'd have to solve the elliptical cylinder. It was 4x squared plus z squared equals 4, and we'll solve this for both x and z. So if I solve this for z, I get z squared is equal to 4 minus 4x squared, or z is equal to plus or minus initially, but we just want the positive value, so I'll just put the positive root there. 4 minus 4x squared, or if you like, you could factor out a 2 from that radical. That's if we solved it for, that would describe this boundary curve right here if we'd solved it for z. So we're thinking of it z as a function of x, or we pick an x value and then find the appropriate z value. Okay. The other way we could solve this is if we solve this for x squared here, or solve this for x, so we'd have 4x squared is equal to 4 minus z squared. Dividing everything by 4 and then taking the appropriate positive root of this would give me the square root of 4 minus z squared all over 2. Is everyone okay with that? So that's another way of describing that curve there. Okay, the other planes that we could project into is we could project into the YZ plane. Let me do that in the same color. Okay, so in this case, what we're going to think of doing is we're going to think of shining a light along somewhere in the distance along our x-axis, and that's going to make a shadow onto the YZ plane there. Okay. Now, the edge along that YZ plane that you're going to get is going to be the shadow of that edge right there as it gets projected onto the YZ plane. Well, where is that? That edge right there is the intersection of this boundary line and this boundary line. Anyway, you can kind of imagine that shadow right off the bat, but if you don't see that, I'll explain how to get this shape in just a moment. But you can kind of imagine that shadow, again, as I'm shining this light along the, down the x-axis, it projects that shadow into the YZ plane. Okay, so there's our region here, and what would describe that? Well, as I said, this boundary right here, well, let's go ahead and put our coordinates on here. That top point, and by the way, Matt asked about the coordinates, so let me go ahead and put that in. These coordinates right here, this would be the coordinate, this would be in 3 space the coordinate 0, 0, 2, and this would be in 3 space the coordinates 1, 0, 0. This would be, of course, the coordinates 0, 0, 0, as always. And then this one would be the coordinates 1, 1, 0. And we get that because this is the point where the line y equals x hits the line x equals 1. And so y must be 1 as well. So folks, real quick, are there any questions so far? Please stop me if you have questions. Okay, thank you. We'll move on. So this would be the coordinates here in the the YZ plane. Again, we're imagining shining a light down here, and so this would be the coordinates where y is 1 and z is 0, and up here we have z is 2 and y is 0. And then what is this line right here? I mean, I think we could all agree that that's the plane y equals 0 and that's the plane z equals 0. There's nothing really interesting there. But this line right here is where this red line that I've sketched right here, that's where it gets projected into the YZ plane if I'm doing this shadow method where I'm shining a light down the x-axis. So that's where this curve meets this curve, and so what I can do is simply replace the x squared in this curve, or in this curve because it's on the xy plane or YZ plane, with this curve where y equals x. Okay, or if you want to think about a plane and surface, that works as well too. So that would be when 4y squared plus z squared equals 4, and if I solve this for z, I get almost the same thing as before. I get 2 square root of 1 minus y squared, or if I solve it for y, I get the same thing as before, essentially 4 minus z squared all over 4. So those are the two different ways we'll be describing that upper curve there.
Is it over 2?
Oh, excuse me. Yep, that should be over 2. Thank you, Hannah, or Hosanna. Thank you. Great. Somebody else was going to say something. Were they going to say the same thing? All right. Great. Okay. So the last one then. So again, we're projecting this into the 3 different planes in our coordinate system, 3 different positive planes. So if we were to project this into the xy plane, and notice of all of these, 2 of them, the shadows are sort of already there for this particular shape. They're already sitting in the plane. But again, this would work even if we had, I wouldn't write this down, but even if this solid were sitting way up here, up higher, we've got this solid here. If we shined a light down, it would make some sort of shadow in that xy plane. Okay, so in the xy plane, this shape would look like this. And we see that in the image I was given, but we could also see that from the information that we have here, given that this is where, so this boundary right here is where this curve intersects the x-plane, which is where z equals 0, so that happens at x equals 1, and where this plane intersects the xy plane, and that happens along the line y equals x. Okay? So of all of these, this is probably the easiest to describe. In just the xy plane here, so again, I'm just restricting myself to the xy plane, we've got 1 comma 0 and 1 comma 1, and I guess I haven't been labeling the origins, but there's that. And the only interesting line to talk about here is the line y equals x or the line x equals y, same thing. Folks, hopefully you know that this is easier said than done, what I just did here, sketching these 3 traces. Okay? This required some work. Okay? So that's what you need to practice more of. If there's something I'd say folks need to practice more of, it's sketching these regions, or being able to interpret this information here to come up with these regions in the xy plane where possible. Okay? But what I'd like to do now is let's go ahead and find each of these 6 iterated integrals. Okay? And this is the part where I think by doing all 6 of them, we might have a better sense of what's going on, rather than previously I've just done 1, 2, or 3 of them. In this case, this one will work easily for doing all 6. There's nothing, you don't have to break any of these integrals up, so this one will work well for that. So let's go ahead and give this a shot. All right. what I'd like to do here is for each one of these problems, I'm going to put a red dot. Now, I know that I don't know where it looks like that red dot is, but I want you to imagine that red dot is somewhere inside the surface. Sorry, inside the solid, not necessarily on the edge, not necessarily on the boundary of this solid, but somewhere inside of it is where I'd like you to imagine it. And once I draw some arrows, it will look like it's sitting interior to the solid, once we draw some arrows on it. So the first iterated integral that we want to do is dx, dy, dz. Now, as far as the order of integration goes, we know that we're supposed to work with the innermost integral and then work our way out, correct? That's how we do the evaluation. But I think that when it comes time to assigning the limits, it makes more sense to work from the outer integral in for assigning the limits. So the outermost integral in this case is dz, and the next one is dy, so that's going to put me where for my region? If I wanted to think of this as, and I'll only write this for this one of them, if I wanted to think of this as the double integral of r and then have the innermost integral, the innermost integral would be dx, and then my dA would encapsulate the dy dz there. And so my r is the region in which plane, folks? It's the region in the zy plane. And the order that I gave that there is moderately important in that I'm thinking about z as the independent axis and then y as the dependent axis. What I'm not going to do is redraw this picture, this picture right here. So don't write this down. It's not going to be very helpful for us. Our diagram's already getting cluttered. But really, if I wanted to think about this as the zy plane, I would write it like this. Here would be the coordinates 2, 0. Here would be the coordinate 0, 1. Again, where I've reordered the coordinates in terms of independent, dependent. Okay, but it's not really worth drawing all 6 of these, but that's how I'm thinking about this very first one. Okay, so this is the part where I think I've got something I can show you with these problems. What I'd like to do is for my first integral here, I'm going to use this first picture, and we've got dx, dy, dz, so I'm going to work from outside in choosing my limits. Okay, so first I'm going to say I need to go up to some fixed z value to get to that point. Okay. Well, how could those z values run? They could run anywhere along that z-axis, so those z values are free to run anywhere between a z value of 0 and a z value of what? Z value of 0 and a z value of what, folks? Good? Everyone okay with that? So the z values can run between 0. Here I'm going to try to write this in here as nicely as I can. Z equals 0 to z equals 2. Okay. Then what do I do? Well, in the order of integration, we then, after we've selected a z value between 0 and 2, we then go and select a y value and fix that y value. So what I'm going to do now is I'm going to come out let's see, that should be parallel to the y-axis. That should come out some y value here. To get to my point. Well, what can my y values range from? Here's where having this trace plane is going to be helpful, because the z values could run anywhere between 0 and 2. So we did, here we had z running up like this between 0 and 2. And then we run out some y value until when, folks? These y values can run all the way out until I hit this curve right here. This curve, if I think about it as a function of z, is this curve right here. So again, these y values have to, they're trapped by the fact that they've got to lie somewhere in the shadow region of that space right there, when we project us into the YZ plane. So my y values are free to run how? And here's where, I think these pictures get cluttered and it's sometimes hard to see what's going on here. This is why having drawn that region as just a plane is much easier. My y values can range anywhere between 0, because notice all these arrows would start at 0. So they would all start at 0, so from y equals 0 up until y equals, and we hit that curve there, and that's the curve, the square root of 4 minus z squared all over 2. Now what do we do once we've fixed a y value? So we've fixed some z value, we've gone up to along the green arrow, and then we go out along the blue arrow to some fixed y value, and we're trying to get to that point that's sitting there in space, right? So we're trying to get to that point that's sitting there in space, and the last thing we're going to do is we're going to run along the x-axis until we hit that point. Until we hit that point there. Okay? Now here's where you have to be a little bit careful, I think. Notice we don't, if you can imagine this in 3 dimensions, which is hard to do, but notice I don't actually start intersecting the region until I pass that beige plane. You guys see that it's colored beige there, or I don't know, light brown? I don't actually get into my solid until I hit that beige plane, and then I stop including x values when I get to that blue face that's given by the cylinder. So I enter it through the beige plane and I stop when I get to that blue cylinder. So that makes my my x values are going to go from x equals 0. Oh, sorry, that's not right. From x equals, hit the beige plane of y until we hit the blue cylinder, which is the square root of 4 minus z squared all over 2. Let me zoom in on that. Sorry about that. Okay, so folks, what I'd like is kind of some feedback from you. I'm not gonna repeat this one. I'll answer questions if there are any, but what I'll do is I'll move on to the next one, and then we'll see how many people are still struggling with it. Then we'll move on to the next one until we're feeling good, and we'll just keep going until everyone feels good about these problems. So if I get some sort of feedback, you can chat me privately. Still a little fuzzy. Give me some sort of feedback for how we're doing. Thank you, folks. Thank you. Yeah, we're going to do at least one more, Matt. No worries. Good. Okay, so let's do another one here. So this next one will go a little bit easier, I think. So for this next one, I'm going to look at this next integral here where I'm going to do the order. Well, as far as I integrate, I go dx, dy, dz. That's the order of integration. But when it comes time to assigning the limits, I'm going to start with thinking about going along the y-axis. So look how the picture changes here, folks. When I integrate with respect, so let me go ahead and put that order in there. The order was, what did I say, dx, dz, dy. So we got dx, dz, dy. So I'm going to go out the y-axis first to get to the point. Then I'm going to go, so that was the y-axis. Then I'm going to go up the z-axis. So I'm going to go up the z-axis to get to the point. And then I'm going to go out the x-axis until I arrive at that point. Okay? So that's how we're getting to the point when we do this order of integration. We first fix a y value, and we run through all of our z's. So we get to the z value we want. Okay? And then for that fixed z value, we then run through all of our x's. And so to get to that point, we just keep going until we arrive at the appropriate x value. Okay? So let's take a look here. So we're integrating with respect to y. So what are our y values? They're the ones that are most free in this problem. They're free to run anywhere between here and whatever this point is right here. Well, that's y equals 1. Okay? So the y values are free to run from y equals 0 to y equals 1. Notice that the limits on integration, I didn't just change them. And that's where I think a lot of you are making mistakes. I didn't just change these limits of integration. Okay? I've got a brand new way of describing the address of this point, and I've got to be consistent with that brand new way of describing its address. Okay? So my y values range between y equals 0 and y equals 1, and then I do my dz, so I'm going up. Now what can the z values do? Well, they can go anywhere until I hit, so again, in our YZ plane there, I can go until I hit that blue curve in the YZ plane. Okay. This is where I really do think that having this region, so this was, if we called this problem part A, maybe this was what we did to get to part A. So for part B, we're still going to be in the YZ plane. Do you see that? Because we still got the Z and Y there. But in this case, I'm going to go out. For part B, I'm going to go out some y value and then up some z value. Okay, so that's what we're doing here for part B. So I go until I hit that curve, and in this case, I'm going from z values of 0 up to z values of, and then when we hit this curve, so we're going to describe that as the square root of 4 minus z squared. Oh, excuse me, that's not right. We're going to describe that as, come on, get out of my way. Sorry, my, z equals 2 square root of 1 minus y squared. Yeah, that's it. Yeah, it looks like I had a chat. Let's see here. Oh, maybe not. I don't know why sometimes I get this delay. When I'm working on my tablet screen, I get the chats they come in a delay. So anyway, all right. So again, when I integrate dy, again, the order is dx, dz, dy. So I'm going to talk about picking a y value, then moving up till I hit an appropriate z value, and then going out until I arrive at the x value. So I'm first going to go out, and my y is free to range anywhere between 0 and 1, all the y values it normally could take on. But then my z, I've got to be restricted to the region in the yz plane. So I can only go up until I hit this curve now. Now I'm going to go out in the x, and I'm going to start picking up x values when I hit the beige plane, and I'll stop when I hit the blue cylinder. So that part didn't change, right? Does everyone see that? That part didn't change. We're still going to go from x equals y to x equals the square root of 4 minus z squared all over 2. So folks, there is no real shortcutting this. I mean, you can get faster at it. I'm spending a lot of time talking about it. You don't necessarily, depending on your order of integration, you don't have to draw all 3 planes like I did here. Okay? So you can certainly get faster at this, but I don't think there's any way to shortcut this. I don't think you can say, well, in the previous problem, this is how I did it, so in this problem, I'll do it the same way. I think each time you've got to be thinking through these limits of integration, and that's the most challenging part of this, in my opinion. So could I get some feedback, some thumbs up, thumbs down, private message or public message, whatever works well for you? Good. Yeah, we're just going to keep, I know the pictures are really messy, but we'll just keep doing it a couple more times. Yeah. Thank you, folks. Okay, so now let's do actually one where the outer integral, or the innermost integral has changed. So now we're going to do dy dx dz. So for this one, we're going to do dy dx dz. Okay. So in this case, I get to move all the way along here for my z values. Okay. Again, the order of integration goes dy dx dz, so I think of first going out to a particular z value, then out to a particular x value, and then finally out a particular y value. Okay. So now I'm going to move along the x-axis to some x value, and then I'm going to go out the z-axis, or excuse me, the y-axis until I hit that point. So folks, if you haven't picked up on this, I probably should have said this. In this diagram, I'm using green for my outermost integral. I'm using blue for the middle integral, and I'm using that orange for the innermost integral. Okay. So what I'd like everyone to do is now go ahead and identify what the limits of integration are for that particular integral. Okay, so go ahead and identify those limits of integration. I think it's a little bit hard doing it all in this three-space diagram. So decide which of these three planes you're using as your R, that outer region. Which of those three planes applies in this case? And then go ahead and set up your limits of integration. I'll work at 2, and we'll give it a shot. Okay. If you feel good about that one, if you could send me a chat or give me a thumbs up, and then move on to the next one. Oh, that should be z equals 2. Thank you, Kevin.
I did that one right, but I kind of contemplated going for the bounds of y. Because I feel like I could interpret it as going from that curve, like the y equals square root of 4 minus z squared over 2, to y equals x.
So look at this. Oh, that's, yeah, so we're not on that curve there, and I'm sorry it looks that way. Let me see if I can kind of, I'm not going to change anything, folks, but let me just see if I can sketch that a little differently. So let me put the point kind of, give myself a little more room there. So if we go up the z-axis, and then we go, so do you see that that's running exactly up the z-axis, right?
Yeah. Yeah.
Now we're running exactly, actually I think I need to go up a little higher to make that work.
Along the x.
Then we're going along the x-axis, but at a particular height now. Mm-hmm. So we're going along the x-axis now to here, and I don't quite make it, I'm not going to that surface. I'm not going all the way out to the surface for this interior point.
Right.
If it was a point on the surface, I certainly would go all the way to the edge of it. But for that interior point, I'm stopping a little bit before that in order to then turn 90 degrees and go along the y direction. So where could those go to? Well, they could start here and they would stop as soon as I hit that beige plane. So that's where they're stopping. That's when you exit the, you start when y equals 0, you start in your solid, just because this one's already butted against the xz plane. But if it wasn't, you'd have to wait until you intersected that solid. But we intersect the solid right at y equals 0, but we stop intersecting the solid when we get to y equals x, that beige plane there. Yeah, that's where this picture part isn't quite perfect. But I mean, it's the correct idea, but then you're going to actually use, sort of your intuition, and you're going to use these just x, y, the paired planes for other aspects of it. Yeah.
Right. And could you also just see, like, in the text that it says the planes y equals 0? I don't know.
Yeah, you can do that, but again, you got to kind of be careful in how you describe these things. For example, that's the plane y equals x, but sometimes we'll refer to it as the plane x equals y. So that's where you got to be careful. It just depends on context as we're doing our iterated integrals.
Okay.
Yeah, great questions. Other questions on this, folks?
In this one, for the x part of the integral, wouldn't it be bounded by the drawing of the zx plane that we did?
That's true. So let's go ahead and label this one. This is option C here. So for C, our region, our region is given by these two outermost integrals, right?
Oh, wait, hold on. I forgot that we had two equations for that one.
Bingo.
Yeah. I drew mine a little different than yours, so I was in a different spot.
No worries.
I see it now.
No worries, but let's go ahead and talk about it anyway. This tells me that R is in the Z, actually technically it's the ZX plane. Okay? But what I'm going to do is I'm going to go up some Z value for part C. I'm going to go up some Z value, and then my X values are going to range between here and here. So this is for part C. That's the way we're doing it. So in fact, I think I might be able to get away with a large, let's go ahead and do D. We're going to do D a little bit faster now. So for part D, notice I'm still in the XZ plane. So for D, I'm going to go out the X direction. So X is free to range anywhere between X equals 0 and X equals 1. Then I'm going to go up in the Z direction, and those Z values are free to range anywhere from Z equals 0 until I hit the curve, and that's the curve Z equals 2 square root of 1 minus X squared. Okay. So then the next thing to do is to imagine, however you wish, and this is probably the hardest part, is, okay, we're now in the XZ plane here. So where are the Y values going to go from? So the Y values will run from the XZ plane right at Y equals 0 until we hit that dot, and those dots would stop when we hit that beige face. So that's going to go from, again, Y equals 0 to Y equals X. Okay, I can't tell if I had a chat or not. It's so weird that they come up so late. Great, thank you. Okay. So folks, given that, I'd like you to go ahead and try the last two. Okay. Once you get done with that, let me know. Please just send me a chat that says I'm done. If you are completely lost at this point, let me know. Just give me a chat or give me a deer in the headlights, whatever you're comfortable with. Because this is tough, folks. This is, it's something that it's going to get easier as you get comfortable with it, but I know that a lot of you are really struggling with this part of it. So please don't feel bad if you're struggling with this. This is the hardest part of this this triple integral, I think, is trying to imagine these pieces. Everything else is kind of using your Calc 1 knowledge and maybe putting in new coordinates. But this is the hardest part.
Can you show that third triple iterated integral real quick? Again.
The third one? C or D?
D.
D.
Or no, the fourth one, yeah.
No worries. I don't know why that's so lagging behind. There we go.
I feel like I could just get confused on, like, I could do the first two integrals,
Great.
And then the last one is really hard. I don't know why, but I can't picture where it goes for, like, for dz.
Mm-hmm.
I feel like it starts at 0 and goes up to that blue surface.
And so what I'm going to recommend is that you go to our textbook here. Let's look at page 1038. So here you've got a much better example of how they're talking about, first running along the, so this, let's go ahead and see if we can interpret this. And my mouse isn't going to, or my pen isn't going to look good here. Let's just grab a different color. Purple. So so notice that they've drawn this a little bit differently because this one doesn't start at x equals 0. It starts at x equals a and it stops at x equals b. But we're first free to pick a value running along the x-axis. So those go from, those go from x equals a to x equals b. But then we need to, once we've picked one of those x values, we're going to go until we hit the region in the xy plane. That's because our region is xy. So we're going to start at the lower limit and stop at the upper limit. Now it sounds like you're doing well with those two.
Yeah.
But then the hard part is, and this is tough visualizing it, and maybe better drawings would work better. But then we're going to say, okay, when do we actually take a point from inside here, which isn't our solid space at all in this case, right? This point right here isn't our solid space at all. But when does it?
The blue thing.
Yeah, the solid space is bounded between the blue and the orange, blue and yellow cups, whatever those are.
Yeah. Okay.
That's where you're going to start picking up z values, and you'll stop when you'll hit here. And in that case, this is given by this thing's in my way. This lower function down here and this upper function up here. So h of xy describes this yellow cup, and g of xy is what's describing this blue cup.
Okay.
If you go a little bit further in the book, let me zoom out here. You can get a whole bunch of images that you could start thinking about. Okay, so in this case, let's look at this one here, which is best integrated in probably polar. This one was actually taught before we learned cylindrical coordinates, so you can do it, just doing polar and z, but that really is cylindrical. But our region is here, so you go out a particular x value, then you go out to a particular y value, and then you're going to go up until you enter the surface, which is maybe right here. You start entering the surface until you exit the surface, which is maybe right here. Again, there's sort of some limitations on my ability to draw these. But what I just did is incredibly important, so I recommend that you practice that a few times. Just grab a whole bunch of different images from the book.
So in that case, your z's wouldn't be at 0. It would be at, like, the function that describes that cone.
The lower cone, exactly. And you would stop when you got to the function, and you'd have to solve for that in terms of z when you hit that upper bowl. Paraboloid, I guess. Sphere, that's a sphere. Yeah, great. Keep going, folks. Whoever's asking the most questions is going to be learning the most. Keep asking questions. So let me go ahead and put, with that in mind, now that we've kind of discussed that with a couple of images, let's look at these last two questions here. Okay, so the last one, we're in the YZ plane here. And based on the order of integration, we're going to go, so I'm looking at, let's see, we did D, so let's call this letter E here. So for letter E, we're going to first go up in the Y direction, and then we're going to go out in the blue direction. That's the X direction there. And so what are we doing? Well, our Y values are free to range from Y equals 0 to Y equals 1. Now our X values are free to go from, well, not until I actually enter that region, right? My region is shaded in green there, so I don't want to start taking x values until I get into that region. So where's the boundary for the region as I'm going in this order? It's that line there, that line y equals x. So we're going to go, for blue, we're going to go from x equals y, and we're going to stop when we always stop when we hit what? X equals 1. Okay. Now for our z, that that part's each time it's a little bit different, but let's see here. We went oh, and sorry, let me label that with E here. E was that order. And so for E here, we're going to go out a y, and then we're going to go out an x. Let's go ahead and let's make that a little bit closer to the center. So we'll go out a y, and then we'll go out an x. So we start picking up x values once we pass through that beige plane, right? We're not in the solid until we've passed through the beige plane where y equals x. Then we're in the solid until we hit the blue curve here. So this part right here, my x values have to range between the beige plane and stop at the line where x equals 1. But then we pick some, for some xy pair inside of there. So that's an xy point. We'll go up until we hit the blue cylinder. So when do we hit the blue cylinder? Well, the blue cylinder values are going to start at z equals 0. And they're going to stop when we hit z is equal to, and now we need to describe the cylinder, excuse me, in terms of x, because we've picked a x and y ordered pair. And then let's do the last one here just for completion's sake. So you've got them all and you can then practice this. Okay? So what I highly, highly recommend you do is you print off a couple of blank pages, or a couple of, just reprint out this first page a couple of times and practice this once a day for the next couple weeks until you just feel really comfortable with it. Okay? So let's look at f here. So for f, we've got dx and dy. So that we're in the xy plane. And so we're going to first go out a particular x value and then up a particular y value. So I can see then that my x values are free to range from x equals 0 to x equals 1. My y values start at 0 but stop when I hit the line y equals x. And then notice that so here's a little bit of a hint, that innermost value hasn't changed any, so we can use the same description from before, because we're in our xy plane still, and now we go up from z equals 0 up until we hit the cylinder, which is the cylinder z equals 2 square root of 1 minus x squared. Folks, I think the wrong way to try to do these problems is to look at some sort of pattern in those limits of integration. You're going to get yourself in trouble if you're trying to search for some sort of pattern in them. Instead, you have to think of it in this iterative process that I did. There are other ways you can think about this, but I think this is the easiest one in this case. Okay? Folks, this is tough. You need to practice it. This is tough. It's not going to get any harder than this.